Hello everyone, welcome back. So the problem of the day is from the topic of motional EMF, and a very similar but easier question has appeared in INPHO 2017. Okay, so firstly we are going to solve this problem, and let's read the problem statement first. So we have a uniform thin rod whose length is L and whose resistance is given to be capital R. And as we can see, it is constrained to move on a vertically smooth track at the end A and a horizontally smooth track at the end B. The resistance of the rail can be ignored. Assume that there is a uniform magnetic field in the direction shown in the figure. So it is coming out of the page. At the beginning, the azimuth angle or the azimuthal angle of the thin rod is phi equal to 0. Okay, so judging by the diagram, so initially the rod would be something like this. Basically, the angle that they're talking about is this particular angle. After the thin rod is released from the static state, it immediately slides down. When the azimuth angle reaches phi, the downward speed of the end A is measured to be VA. So they're saying at this general phi, this point A has a speed of VA. So yeah, and that's the given situation. Okay, so the first question is we have to find the magnitude of the electromotive force EAB between the ends A and B of the thin rod and determine which end has a higher potential. Okay, so let's start with this problem first. Okay, so first we are going to find the EMF EAB due to the motion of the conductor. So now there is two ways that we can go about this problem. Okay, so first we'll use the straightforward method. Okay, finding the EMF as the negative rate of change of the magnetic flux through a loop. Okay, and that loop will decide which loop we are going to take. But so yeah, this we can call the flux rule, or we can also call it as Faraday's law, right? So we are going to be applying Faraday's law in this loop OAB. Okay, so now I'm going to consider the area vector of the loop be in the outward direction, such that the magnetic flux through this right triangle through the loop OAB is actually positive. So let's find the magnetic flux through the loop OAB. So this is just a right triangle, so we can use half BH, right? So this becomes L square by 4 sine 2 phi. Okay, so it is basically L cos phi, L sine phi multiplied by half. The sine phi cos phi I wrote it as sine 2 phi by 2, and we have the area as L square by 4 sine 2 phi. Now the area vector multiplied with the magnetic field will give us the magnetic flux, and as they are pointing in the same direction, the flux is positive. Okay, so yeah, now we have the flux as a function of phi. Now the induced EMF is just the negative rate of change of the flux. Okay, so now what does positive EMF mean and what does negative EMF mean, right? Because at the end, it's just a scalar equation. So firstly, we took the area vector to be positive in the outward direction. So a positive value for the EMF would mean that the induced current will be in the counterclockwise sense. So basically, if you curl your fingers in this direction, then the thumb will point the outward direction, which is parallel to the area vector, right? So this corresponds to the positive EMF case. So if you observe, positive EMF occurs when d phi by dt is negative, right? So if the flux through the loop is decreasing with respect to time, then what happens is currents will be induced in the clockwise sense. And if, for example, let's say d phi by dt is positive, then currents will be induced in the opposite sense. Okay. So yeah, that's basically what the rule states. So now let's just calculate E. So we'll just have to differentiate this with respect to time and put a minus sign in front. So this is going to be minus BL square by 2 cos 2 phi multiplied by d phi by dt. Okay, so now guys, phi dot d phi by dt is the rate of change of this particular angle. And if you observe, the rate of change of this angle phi is nothing but the angular velocity of the rod itself, right? Okay, so I'm just going to call it as phi dot for now. So phi dot, we can also say it is the angular velocity of the rigid body. So now in order to find the angular velocity of the rigid body, we can take the help of the instantaneous axis of rotation, right? So how do we locate that? So we know that the point A is moving in the vertically downward direction, and the point B, which is on the ground, is constrained to move in the x direction. So if I draw perpendiculars to these two velocity vectors, their intersection at this instant should give me the instantaneous axis of rotation. So that's what I'm going to do. So I draw a perpendicular from here, then I draw a perpendicular from here. Their intersection is the ICR. Okay, so now the use of the ICR, now the use of the instantaneous center of rotation is that we can consider this rigid rod to be performing a fixed axis rotation at this instant about this axis. Okay, so we know the velocity of the point A is given to us as VA, right? So this distance is going to be L sine phi. So with this information, I can write that the angular velocity, and let's say the angular velocity of the rod is omega. So, and we can see it is in the counterclockwise sense, right? So we can say omega is nothing but VA divided by the distance from the axis of rotation, which is L sine phi. Okay, and omega, we can also say it is equal to phi dot. So now we can just substitute it over here. This as the expression for the induced EMF. Okay, so there is a cos 2 phi. So basically when phi reaches the value of 45 degrees, right, the cos 2 phi will become 0, or we can say that the induced EMF is 0. Okay, and if phi is greater than 45 degree, cos 2 phi will be negative, or the induced EMF is positive, and the induced EMF will be negative when phi is less than 45 degrees. Okay, so this is basically the pattern that we are seeing. So, okay, so in order to determine which point A or B is at higher potential, we would need to know what is the value of phi. So initially, now from here we can see that when phi is less than 45, actually tells us about the initial part of the motion, the induced EMF turns out to be negative. So what that means is, so the positive direction of the induced EMF is in the counterclockwise sense, right? And this once again was using the area vector logic. So the negative direction will be in the clockwise sense. So initially the induced current will be in the clockwise sense. Okay, and in order to run a clockwise current, the potential at end A should be greater than the potential at end B. Now, once again, guys, there won't be any induced EMF on these rails, right? Because they are actually stationary. In order for the EMF to generate, the conductor has to move. There needs to be motion of the conductor, and the only moving conductor here is the rod that is sliding down, right? So the EMF will be generated only across this rod. And for the E less than 0 case, VA is greater than VB. And for the E equal to 0 case, VA will be equal to VB. And for the positive EMF case, it means that the current, induced current, will be counterclockwise, trying to support the magnetic field. So that means that VB has to be greater than VA. So in the E positive case, B is going to be at a higher potential. Okay, so basically this is the magnitude, and the direction is and the direction actually depends on the angle phi. Okay, so that was the answer to the first question. And the second question, we have been asked, verify that the negative power provided by the Ampere force is exactly equal to the power consumed by the thin rod resistance. Now, as the rod has some resistance, we know that there is going to be heat dissipation from the resistor, right? Now, the Ampere force is the IDL cross B force because of a current flowing through it, right? So they're saying the negative power due to this force, we have to prove it is equal to the power consumed by the rod resistance. Okay, so now the power dissipation across the resistor is pretty easy to find. So the current, so firstly, the current through the resistor is the EMF generated divided by the resistance, right? Which will be equal to this particular value. So we can easily find the power dissipated across the resistor. So the power dissipated would be just the current multiplied by the voltage. So now I'm going to just leave the EMF in the form without substituting the omega, because that looks a bit more cleaner, right? Okay, so after substitution, we'll get the instantaneous power dissipated across the resistor as this particular expression. So now we have to talk about the instantaneous power of the Ampere force. So I'm just considering the initial case where the current was flowing in the clockwise sense. So in the conductor, the current actually flows from the point A to the point B. Now so if I take a small segment of the conductor, okay, so and I'm saying that the length of this segment is dl, then the Ampere force acting on this segment is given by the expression of the current times dl vector cross b vector. So here dl vector is considered to be a vector whose magnitude is equal to the length of the segment, and it's in the direction of the current flow. In this tiny element that we just figured out, dl vector is in the direction of AB, right? And the magnetic field is out of the page. So if you do dl vector cross b vector, the direction of the Ampere force turns out to be in this perpendicular direction. Okay, so this is the direction of df. Okay, so here the interesting idea is, doesn't matter which tiny element of the conductor you take, the Ampere force will always be in the perpendicular direction. So now we know that in order to find the power of this force df, I have to find the dot product of f dot v. Okay, and here the velocity, here the v vector is the velocity of the point under consideration. Now this small tiny segment that we're talking about is under general planar motion. So it can have vy and vx both, right? But we don't have to make it complicated because we know the direction of the force, right? It's in this direction. So we can actually simplify it a bit by considering a velocity in the normal direction, and a velocity in the parallel direction. So instead of writing vx and vy, we'll write a normal velocity and a tangential velocity for our DL element. Okay, and the use of doing this is that because of this Vt, there won't be any power, right? Because we'll write V vector as Vn in the n cap and Vt in the t cap, right? N is in the normal direction, T is in the t direction, okay? Tangential or along the rod. So here obviously as F is in the normal direction, the answer just will be dF multiplied by Vn. So I'm just going to consider this direction normal to the rod as n cap. So this would just be equal to dF multiplied by V normal. Instead of, I just broke the dot product into scalars. Okay, so now what's the magnitude of dF? So that will be the current multiplied by this cross product. Now this cross product is easy to figure out. DL is along the AB direction and B vector is out of the pitch. So the angle between DL and B is 90 degrees. So this would just be IDLB, right? So this is going to be B DL multiplied by Vn. So this is what dP has turned out to be so far. So if I want to find out the total power dissipated by the Ampere force, it will be just the integral of this, right? So we have to integrate. So as we are talking about this particular instant, the current is a constant, so we can take it out of the integral. And basically we'll have to integrate Vn dl. Okay, so in short, take elements, find the normal velocity and multiply it with the length, right? Now, okay, so now here if you observe, this is very similar to the COM result, right? The velocity of the velocity of the center of mass in any particular direction, we define the velocity of the center of mass as integral of V dm. So basically we choose break down the entire body into small dm masses, multiply it with the velocity vector and divide it with the total mass, right? So this is how we found out the velocity of the center of mass. Now this is pretty similar. So I can convert this into the similar center of mass formula. All I have to do is multiply it with the linear mass density of the body, of the rod, right? So this will be IB divided by lambda times integral of the normal velocity multiplied by dm. So now from this relation, the integral of V dm is nothing but the velocity of the center of mass multiplied with the total mass. So this would just break down into IB total mass by lambda multiplied by velocity of the center of mass. But what's more important is it is in the normal direction. So we're talking about the normal component of the velocity of the center of mass. So basically we don't have to do any integral. All we have to do is locate the center of mass, which will be somewhere over here, and find out the normal component of velocity. Now for this, we can take the help of the instantaneous axis of rotation, okay, and a little bit of geometry. So once again, let's just locate it. Okay, so this is the location of the ICOR. In order to find the velocity of the center of mass, we'll draw a position vector to the velocity of the center of mass. Okay, so now the velocity of this point will be along the normal to this position vector. Because I drew this triangle like an isosceles triangle, it looks as if this is along the line AB, but it does not have to be along the line AB. Okay, so what I'm going to do is I'm going to slightly redraw the diagram. Okay, so I basically drew the triangle like this in order to avoid confusion. Okay, so now this is the location of the ICOR. Now center of mass of the rod will be somewhere over here, right? So now it should be clear that this is not along the rod, right? So this is the velocity of the center of mass. Okay, so now we are going to use a property of right triangle. So first of all, the center of mass is the point that we're talking about is the center of mass of the rod, right? Which is also the centroid of the rod. So basically it's the centroid of this side AB. So this length is L by 2 and this length is also L by 2. Now the property states that if from the vertex of this right triangle, I draw the median to the other side, right? So this is called the median of the side AB, right? Then the thing is, the property is the length of this median is also equal to this L by 2. So even this side length is going to be L by 2. Okay, so now this triangle and this triangle, they are congruent triangles. So which basically means that even this side length is going to be L by 2. Okay, so even this is going to be L by 2. So the velocity of the center of mass is going to be L by 2 omega. Okay, just by the principles of circular motion. Okay, from the earlier expression, we want the normal component of the velocity of the center of mass, right? So for that, we'll have to find some angles. So this angle, if you guys remember, this was initially equal to phi, right? And now this is an isosceles triangle now, right? Which means even this angle is phi. So even this angle is going to be phi. Okay, so basically this thing over here is a rectangle, right? Okay, so basically if I draw a horizontal line here, okay, so these two angles are also going to be phi. So that means this angle is going to be 90 minus phi, right? Okay, so now the thing is, okay, so now the velocity vector is normal to this line, right? And this line makes an angle phi with the vertical. So the velocity vector makes an angle phi with the horizontal. So this angle over here is phi. Okay, so now from here, what is this angle that the velocity vector makes with the rod? Okay, so the pink angle is going to be phi. So from phi, we have to subtract this angle. And this angle is going to be 90 minus phi, right? So this angle is 90 minus phi. Okay, so we have to do phi minus 90 minus phi. So that is going to be 2 phi minus 90. So finally, the velocity vector just makes an angle of 2 phi minus 90 with the rod. So with the normal direction of the rod, it will make an angle of 2 phi. Okay, so basically this is what we were trying to find. Okay, so far what we figured out is, so basically we have the center of mass somewhere over here. Velocity of the center of mass makes an angle 2 phi with the normal direction. Okay, and the velocity of the center of mass, we figured out it was L by 2 omega, because the distance of the center of mass from the ICOR is L by 2. So the normal component, so now we can continue with this expression. So we can just write lambda as mass per unit length. So this will become BIL. And the normal component of the velocity of the center of mass will be L by 2 omega, and the cos component, right? So this component is going to be the cos component of L by 2 omega. Now we can just substitute back the value of omega that we determined earlier. Okay, so now let's substitute the value of current back into this expression. Okay, and once we substitute the value of current into this expression, we'll get the answer as this particular value. Okay, which actually in terms of magnitude matches up with the power dissipated across the resistor. So I mean, that's what we had to prove in this question. Okay, so now what is this question trying to tell us intuitively? So let's try to understand that. Okay, so basically what happens is once the rod starts rotating, right, with some angular velocity of omega, we know that an EMF is induced. Okay, and why is the EMF induced? It's because the magnetic Lorentz force, the magnetic force component of the Lorentz force, which is QV cross B, right, acts on the individual charge carriers in the rod, and it will push the electrons along this conducting loop. Okay, and that's the reason why an induced current is generated in the first place. Okay, but the thing is, magnetic forces by definition does not do any work, because the magnetic Lorentz force acting on any charge, any individual charge particle, is actually QV cross B, right? And here V is the resultant velocity vector of the particle. So if you try to calculate its work, so we'll have to dot product this force with the displacement vector, right? But displacement vector is in the direction of the velocity vector. So this cross product is perpendicular to the velocity vector, and ds is parallel to the velocity vector. So which means V cross B vector and ds vector are perpendicular to each other, which means this actually turns out to be 0, which means that dot product turns out to be 0. So magnetic forces by definition won't do any work on this conductor. But when we talk about induced EMF, we see that the charges are being pushed around the conductor, right? So obviously, drawing analogy from the current electricity chapter, we know that the battery does some work, right? So similarly, this induced EMF is doing some work, and clearly it does. Okay, so does that mean it's a contradiction? So why is that happening? Let's try to understand that. So if I take a very tiny element in the conductor whose charge is some dq, okay, so as it is moving in a plane, so in general plane motion, we'll consider two velocity components. So let's say one velocity component is along the rod, and let's call it V parallel, and another component is in the perpendicular direction, let's call it V perpendicular. So now if you try to look at the Lorentz force components, which is Q V cross B, we can write V cross B as V parallel plus V perpendicular. Now these are in vector form, guys. This is not a scalar form, but just understand that. But if we cross product it with B, this V parallel cross B will give us a component perpendicular to the rod. So let's use a different color to represent that. So if you observe this V parallel, if you cross it with B, B vector is out of the page. So if you do V parallel cross B, this is the direction. So this is the direction of V parallel cross B. If you do V perpendicular cross B, it will turn out to be along the conductor, right? So V perpendicular cross B is along the conductor. So this component is what is pushing the electrons along the conductor. Okay, but that is not the total Lorentz force. The total Lorentz force is the combination of this and this. But the thing is, when their combined work should still give us the answer as 0. Okay, now these if you do, okay, so now if you calculate the total Lorentz force acting on the entire rod, this V parallel cross B thing, that becomes our Ampere force. Okay, and this V perpendicular cross B, right, this will be the force that generates our motional EMF. Okay, so now the thing is, if you observe, we've calculated the power due to this Ampere force. So basically all this complicated math that we did for the Ampere force, that was the power of this component, this V parallel cross B component that is perpendicular to the rod. Now, because of this force of V perpendicular cross B, how do we calculate its power? Well, the thing is, this guy is we can indirectly calculate it by saying that this will be the power transmitted, power dissipated across the resistor. So basically, if I consider its equivalent diagram, we can consider a battery and a resistor, right? And we can say that this is the E induced battery, and we can say that the power dissipated across the resistor is equal to E square by R. Power dissipated across the resistor is the same as the power supplied by the battery, right? So we can indirectly say that the power of this force is the same as the power dissipated across the resistor. So taken together, their total power should add up to 0 because of the fact that the total work done by the magnetic field is 0. Okay, so that was basically what question 2 was asking us to prove. Now in question 3, they're talking us about in question 3, we have to find the angular acceleration of the rod when phi is actually 45 degree. Okay, so now the thing is, guys, the phi equal to 45 degree just makes it very easy because at that instant we know that the current in the circuit will be 0. So the torque will only be present because of gravity, right? You don't really have to consider the torque due to Ampere force or anything like that. Okay, so we'll just calculate the angular acceleration for a general angle phi, and then we'll just substitute phi equal to 45 into that. And then we'll just substitute phi equals 45. Okay, so let's take the general phi case, and let's say the current is in the counterclockwise sense. Okay, so now as we have to determine the angular acceleration, there are two ways, right? First is you can go by the dynamics manner, like we'll just calculate the torque of all these forces, torque of all the forces, and set it equal to I alpha, right? But if you're doing it about the center of mass, it's not going to be a very good idea because you'll have to consider the torques of these normal forces, right? Now the thing is, it's easier to just use energy conservation here because we already have the ready-made result for the power dissipated, right? So we can directly use energy conservation, and with the power equation we will get the angular acceleration as well. So that's kind of like a ready-made result. So I will be solving it using that, but the mechanics approach is also very interesting, so I will like to give you guys that as homework. Okay, so now like the mechanics approach, if you want to deep dive into it, then it'll take at least like 15-20 minutes to explain it. I'm just going to briefly discuss it here and give you this as a thinking exercise. Okay, so I'll ask you a few questions and I want you guys to try to answer it in the comments. So our goal is to once again find the angular acceleration. The rate of change of this angle phi is what we defined as omega, right? So let's just say alpha is nothing but d omega by dt, or the double derivative of the angle phi. So I'm just considering alpha also counterclockwise. Okay, similar to how we said omega is counterclockwise. So I'm just assuming it is in the counterclockwise sense. Now here, guys, the center of mass is a terrible point to apply tau equal to alpha, because if you observe, there will be torque, because there will be torques due to normal n1 and n2, and which we haven't determined yet, right? So the center of mass is a terrible point. But what is a nice point here is the ICOR, because if you observe the ICOR, the line of application of n1 and n2 directly passes through the ICOR. So there won't be any torques due to n1 and n2. So we'll only have to consider the torque of mg when we are talking about real torques. But here, this is where it gets a bit conceptual. So here the ICOR, the instantaneous axis of rotation, is an accelerated point. Okay, so now I'm going to give you a wrong explanation, and I want you to explain why is it wrong. Okay, so first of all, guys, here the ICOR is an accelerated point. So you cannot apply tau equals I alpha. So I'm saying the ICOR, let's call the ICR point as m. Okay, so you cannot apply tau about m equal to I about m into alpha. Okay, and the reason lies over here. It's because the ICOR is an accelerated point. Okay, so tau m includes the torque of gravity, by the way. So in this question, the torque of n and n2 will be 0, about the ICOR. So the only external force in this case is the torque of mg and the torque of the Ampere force, right? So you'll have to find the torque of the Ampere force as well. So for a dl element, it was equal to I dl into b, if you guys remember. So you'll have to find the torque. So you'll have to multiply it with this distance and do some calculations. It turns. So first let's write it down. So for it'll include this plus the, I'm just writing it as plus the magnetic force or the Ampere force. So we'll have to consider both of these components in the real torque expression. Okay, but then we also have to include the pseudo torque because the ICOR point is a non-inertial point or an accelerated point here. And together, and these two together, we can write it is equal to the moment of inertia about the axis through m times alpha. Okay, this is something that you can write. But here in this question specifically, it turns out that the pseudo torque actually becomes 0. Okay, and this is what I want you guys to prove. So in order to prove this, you'll have to first find the acceleration of the ICOR. Okay. Okay, so now I'll discuss a common mistake that people make while finding this out. Okay, finding the acceleration of ICOR. Some of you may prove this by using the argument that okay, the center of mass is at a distance of L by 2, right? And it's a fixed distance from the origin, which means the center of mass will move in a circle of radius L by 2, which is correct, right? Because its distance is constant. So here you have to keep in mind something. So because of the isosceles triangle property, as this angle is phi, this angle is also phi. Okay, but their sense is different if you observe. So here the phi is in the counterclockwise direction. Here the phi is measured in the clockwise direction. So as the center of mass is moving in a circle with respect to the point O, it will have two components. First is the omega square L by 2 component. Okay, so now the angular acceleration, we considered it in the counterclockwise direction. So here which means the angular acceleration of this line will be alpha in the clockwise direction, right? Because of the fact that the phi's are in the opposite sense. So the L by 2 alpha component will be in this direction, right? So this is the acceleration of the center of mass. Some of you may have, okay, so now some of you may have used this argument and may have said that, okay, now this is a rectangle and the ICOR will be at a distance of L from the point O, and which means the ICOR will have two acceleration components. First is omega square L towards the point O and an L alpha in this direction. And then you would say that this is the acceleration of the ICOR. Now, this is actually wrong. Okay, and there isn't anything wrong in the calculations that we did, but there is something conceptually wrong here. Okay, so I'll share you the answer. So the ICOR has an acceleration of omega square L towards the origin, and in the tangential direction, it has 0 acceleration. Okay, and because of this, if you observe the pseudo torque, so the center of mass is somewhere over here. The pseudo torque due to this omega square L is m omega square L towards the ICOR. So if you observe the torque of this m omega square L, it just becomes 0 because it just directly passes through the point M. So here, now for this particular question, the pseudo torque just becomes 0. And that's why you can still apply tau equals I alpha. Okay, the real torques equals Im into alpha. Yeah, so now the question is, why is the tangential acceleration 0? This is something I want you guys to answer. Okay, why is writing the ICOR acceleration like this wrong? Okay, so now coming to the mechanics part. So I just told you guys you can apply tau equal to I alpha in this situation. And because of the fact that the tau p is 0 in this situation, right? So you can just figure out the torque of gravity and FB about the ICOR and find the moment of inertia about the ICOR. This is also pretty easy to find because about the center of mass axis, it is ml square by 12 and this distance is L by 2. So you can just add ml by 2 whole squared, which is ml square by 4, and this is ml square by 3. So Im is also pretty easy to figure out. And yeah, from that you can directly get the angular acceleration. So we don't really need mechanics to solve this. We can just use energy conservation. Okay, so now the advantage of using work energy theorem is that we can ignore the work done by magnetic field completely. So all we have to consider is the work done by gravity. So that will be the change in potential energy, right? And then we'll have the power dissipated across the resistor, right? And that's it. So basically we can say that the work done by gravity, because this is the only external force that is doing any work, this would be equal to the change in kinetic energy of the rigid body plus the heat dissipated across the resistor. Okay, so gravity does some work. It is spent in changing the kinetic energy and the heat transferred from the resistor. Okay, so that's basically how we can look at it. Okay, so now if you just divide by dt on all sides, we can just convert it into the power form as well. So the power of gravity equals the equals dk by dt, which is the rate of change of the kinetic energy of the object, plus dq by dt, which is the power transmitted across the resistor. Okay, now the kinetic energy of the rigid body, we can write it as half I above the instantaneous axis of rotation multiplied by the angular velocity of the rigid body squared. The I above the instantaneous of axis of rotation, we figured it out. It was ml square by 3, right? And this multiplied by omega squared. So now let's find the time derivative dk by dt, ml square by 3 omega, right? So the derivative of omega square is 2 omega multiplied by d omega by dt, right? So d omega by dt, let's just take it as alpha. So this is the time derivative of the kinetic energy. So it is actually, so this is going to be ml square by 3 omega alpha. Now the power dissipated across the resistor, this is something that we figured out earlier. Okay, so now let's talk about the power of gravity. Okay, so for this, we'll just find out the potential energy of the rod. So for that, let's write down the coordinates of the center of mass. So the length of the rod is L, this angle is phi. So these two lengths are L by 2 each, right? And so this distance is going to be L by 2 sine phi. But we are more interested in the y coordinate because we want to write the potential energy, right? So the y coordinate of the center of mass is L by 2 1 minus cos of phi. So the potential energy, so the power of gravity Wmg upon dt, right? So the power of gravity, we can just directly write it as du by dt, which is d by dt of mg L by 2 1 minus cos theta. So now if we just differentiate this will be mg L by 2 sine theta multiplied by d theta by dt. Okay, so I mean this was phi, right? So let's just write it as phi. So it'll be sine phi d phi by dt, which is actually omega. So this is the instantaneous power delivered by the force of gravity. Okay, so from here what we are getting is, okay, so now the original expression for PR was equal to this particular value. Now we can just substitute everything in and solve for alpha. Okay, so this is the general expression that we obtain for alpha. Now, okay, so now they wanted us the alpha at phi equals 45 degrees. So at that point, this expression just becomes 0. So the alpha just turns out to be 3g divided by 2 root 2 L. So this will be the answer to option C.